Hello good people, I'm going to explore the Bronsted-Lowry definition of acids and bases. According to this model, acids are proton donors, while bases are proton acceptors. Recall that a hydrogen ion is just a proton. I'm going to use hydrochloric acid as an example. In an aqueous environment, it will dissociate to give the hydrogen ions and the chloride ions. What happens next? The hydrogen ion from the acid will react with water to give a protonated water molecule. In other words, the water molecule has picked up an extra hydrogen. The way I have written it currently is a little bit awkward, so let me rewrite it. Here we go, H3O plus. This protonated water molecule is also known as a hydronium ion. The hydronium ion dissociates readily to give the hydrogen ion and water back, and so often the hydronium ion is seen as an equivalent of a proton. We will explore this some more later. For now, let me rewrite the overall reaction between hydrochloric acid and water. Hydrochloric acid will react with water to give the hydronium ion and the chloride ion. Note that acids and bases always go in pairs. We cannot have just an acidic reaction or just a basic reaction, but we can have an acid-base reaction. And in this case, hydrochloric acid is the acid, whereas water is the base. What about the products? They are known as the conjugate acid and conjugate base. And in very general terms, we could say that an acid will react with a base to give a conjugate acid and a conjugate base. Note that the Bronsted-Lowry model does not mean that the Arrhenius definition was incorrect. The Bronsted-Lowry model explains what is happening in the background. According to Arrhenius, an acid increases the concentration of hydrogen ions. That is still happening here. The Bronsted-Lowry model simply tells us what happens next. The hydrogen ion will react with water to give the hydronium ion. Now, how does this help us explain ammonia? Because that was the issue with the Arrhenius definition. We could not clearly see where does the hydroxide come from. Let me get rid of this and bring in ammonia. When it comes to a reaction between water and ammonia, it is the water that will act as an acid. It will donate its proton to ammonia, converting ammonia into ammonium, and in the process we will generate a hydroxide ion. The way I have written ammonium is a little bit awkward, so let me fix that. Here we go, NH4 plus. This is the formula for ammonium. Overall, we could write this equation as follows. Water will react with ammonia to give ammonium and a hydroxide ion. Arrhenius definition is not incorrect. Ammonia is indeed increasing the concentration of hydroxide ions. Therefore, it is a base. And once again, we have an acid-base reaction. The water is the acid, the ammonia is the base, and the ammonium and the hydroxide ions are the conjugate acid and conjugate base respectively. The acid has lost a proton or a hydrogen ion to become a conjugate base, whereas the base has gained the hydrogen ion to become a conjugate acid. In summary, the Bronsted-Lowry model of acids and bases does not overrule the Arrhenius definition. It builds upon it. It tells us what is happening in the background. This is an example of good progress of scientific thought. Arrhenius had a definition that explained quite a lot, but not everything. Bronsted and Lowry filled in the gaps. That is all for now, and I will see you on the flip side.